In this video, I'm going to show you how to take the derivative of exponential function, and we also want to see whether a function is increasing or decreasing. So here's our function, 4 times the square root of 9e to the minus x plus 8. Differentiate this for 2 rules that we need to use. Here's one that I'm using for the first time in these videos. So if your function f of x is e to some function of x, because before we've seen e to the x, but here we have e to the minus x. So we have e raised to some function of x. The derivative is the function itself again, so e to the g of x is your function, you have e to the g of x in your derivative, but then you have to multiply it by the derivative of only the exponent, so times g prime of x. So before we had only e to the x, and the derivative of x is 1, so this turned out to be 1. But suppose I have, for instance, e to the x squared. Then my derivative will be e to the x squared again, times the derivative of x squared, which is 2x. So remember to multiply by that derivative. It's like with derivative of logarithmic functions. So derivative of ln g of x is 1 over g of x times g prime of x. It's all a consequence of a chain rule. That's what's being used in all of these cases. Also used in this case, too. Here we have this is a general power rule, but I'm refreshing your memory on. So if your function is g of x raised to the nth power, we use a general power rule. So the derivative f prime is n times that function raised to the n minus 1. That's the power rule that you've used many times. But then, because it's g of x raised to the nth power, not just x, it's multiplied by g prime of x. So both of these are the chain rules specialized to these situations of e to the g of x and g of x raised to a power. So I'm going to use both of these to take the derivative of this function right here. First, I'm going to rewrite it. So I have 4 times 9e to the minus x plus 8 raised to the 1/2 power. So now I can use the general power rule. And what I get is 4 times 1/2, then I have 9 e to the minus x plus 8 to the 1/2 minus 1. And then I have to take the derivative of this and put it out here. Well, the derivative of 8 is 0, so that's not going to contribute anything. And all that's left is 9e to the minus x times the derivative of minus x, which is minus 1. Okay. So there's my derivative, unsimplified. So now to simplify it, first my exponent here, 1/2 minus 1 is equal to minus 1/2. And then I'm going to multiply this and this. So 4 times the half is 2, times 9 is 18, times the minus 1 is minus 18. So I'm going to have a minus 18 out front. And then I have e to the minus x. And then I have the rest of this, 9e to the minus x plus 8, all to the minus 1/2 power. And that is my final answer, simplified as much as possible. Now, I can tell you, just by looking at this derivative, that this function f of x is always decreasing. The reason for that is what we have, because e to any exponential function, e to any function whatsoever as an exponent, is always positive. So e to the minus x is always positive here and here. So everything in here is positive. So we're taking this square root of that and then taking 1 over that. That again is going to be positive. And I mean strictly positive. This is never going to be 0. So everything over here is positive, times e to the minus x, also positive. So all of this is positive, but then it's multiplied by minus 18. So the derivative is strictly less than 0 for all x. So we can conclude that the function f is decreasing on the interval minus infinity to infinity. Now, for other functions, you need to see whether the derivative is equal to 0. Those are critical points. And then you would divide your real number line into regions and check by evaluating your derivative at a point in those regions to see if it's positive or negative, to tell you if it's increasing or decreasing. In this case, it wasn't necessary because this function doesn't have any